Welcome to the video. This video is about work, energy and power, which is a topic for the mechanics unit in A-level physics. Conservation of energy is a key idea in this topic. This law states that energy cannot be something, but it can be something else. Can you complete this sentence? This law states that energy cannot be created or destroyed, but it can be transferred from one form to another. And this means that the total energy of a closed system remains constant. A closed system is one where no energy enters or leaves. Let's have a look at an example. So to start with, we're holding a ball above the ground. We can say that the energy is stored as gravitational potential energy at this height. When the ball is released, the ball falls to the ground, towards the ground, and reduces height. And as it does so, it's reducing its gravitational potential energy. We know from conservation of energy that that energy must be going somewhere. And we know that the ball is increasing its speed and the ball is increasing its kinetic energy. So we've got a situation where as the ball falls, gravitational potential energy is converted to kinetic energy, and just before the bounce we can say that all of the gravitational potential energy that the ball had just before we dropped it is converted to kinetic energy just before the ball bounces. And using our equations we can say that the potential energy that we had just before we dropped the ball, mg delta h, has now all been transferred into kinetic energy. So that amount of energy is now in the form of kinetic energy and is equal to a half mv squared, which is our equation for kinetic energy. So we're saying that gravitational potential energy lost is equal to kinetic energy gained. Let's consider the energy changes for a skydiver. Consider a skydiver falling through the air. If the skydiver has reached terminal velocity, explain what has happened to his kinetic energy and his gravitational potential energy during the skydive. So as he falls, there is a reduction in gravitational potential energy, and that energy has to go somewhere. Initially, the energy went to kinetic energy, but now that he's reached a terminal velocity, the kinetic energy will remain constant, but the gravitational potential energy will continue to decrease. So where's that energy going? The answer is it's going to be work done against the air resistance. And at terminal velocity, the forces are in equilibrium. The weight of the skydiver is balanced by the upwards force of air resistance. And so work needs to be done against the air resistance. So we do have conservation of energy because we've got a decreasing gravitational potential energy, which is equal to the sum of the increase in the kinetic energy and the work done against air resistance. And so in our first example, we ignored air resistance. And that's a reasonable thing to do. The speed would be quite slow and the air resistance will be quite small. And so using this analysis gives us a reasonable approximation. So literally just saying that the gravitational potential energy is all transferred to kinetic energy. It is an approximation, but it's quite a reasonable one to make for slow speeds. When we're considering the skydiver, we do need to consider air resistance because he's going much faster and there will be a significant amount of work done against air resistance. And in fact, as we said, at terminal velocity, the potential energy is all converted into work done, and there's no further increase in kinetic energy. These are the equations that you need for the energy topic. So see if you can find these on your data sheet. So using conservation of energy when dropping objects, if this girl drops the ball from 1 meter, how fast will it be going when it hits the floor? And try and do this now and use the idea that the gravitational potential energy at the top is going to be equal to the kinetic energy at the bottom just before the ball lands. And so the starting point here is to write down mgh equals a half mv squared. And what we can then do is just simplify that. It's the same mass on each side. We can then multiply through by 2, which gets rid of the half there. And we can then square root that. So we get v equals the square root of 2gh. And if we put the values in, we get a velocity of 4.43 meters per second. And we should get the same answer if we try this with Suvat equations. And one that we can try is v squared equals u squared plus 2as. And u is 0 because we're dropping the ball from rest. So v squared equals 2as. And in this case, a is g and s is the height h. So we've got v squared equals 2gh. So we get the same answer using the Suvat equation. This next section is about work done. Work done is the energy transferred when a force moves an object. It is calculated from the force needed to move an object multiplied by the distance moved in the direction of the force. And we've got the work done, delta W equals Fs cos theta. Looking at the diagram there, which just shows pulling a toy tractor along at an angle theta to the horizontal, and the tractor moves a distance s. So there is no movement in the direction of the vertical component F sine theta. So this part of the force does no work. The tractor moves a horizontal distance s. The horizontal component of the force is F cos theta. So the work done is Fs cos theta. Power in watts is the rate of doing work, and so we can calculate it from the work done over the time taken. Here's a question on work and power. A woman pulls a block of wood, as shown there, at an angle of 20 degrees to the horizontal, and uses a force of 40 newtons. If the distance travelled horizontally is 6 meters, calculate the work done by the woman and her power if the journey lasted 20 seconds. And so we'll use the horizontal component of the force to calculate the work done, which is 40 cos 20, and we'll then multiply that by the distance travelled in that direction, which is 6 meters. So we get 40 times 6 times cos 20 degrees, which equals 225.5 joule. So that was the work done, and now the power, which is work done over time taken. So just divide that value by 20 seconds. We get 11.3 watts, or 11 watts to just two significant figures.